So, we have been trying to explain the anomalous normal properties of this high temperature superconductors. So, basically once again just to remind you the phase diagram which is most important to us. So, this is the temperature axis and this is the doping axis which causes superconductivity. So, there is a antiferromagnet antiferromagnetic insulating region and then there is a superconducting region. Let us call it this is antiferromagnetic insulator, we will call it at AFI, and there is a superconducting dome. And if you draw an imaginary line which comes very near to the optimal doping point where the Tc is high, this region of the phase diagram should have been a metal, but it is a very strange metal. It does not follow any of the characteristics which have been given out or which have been proposed by the Fermi liquid theory to describe metals. This is almost a metal, it is nearly a very good metal. So, we do not need to worry about. So, this is the region that we are interested in. Maybe we can just draw a bit of shading here. So, that is the region that we are interested in, and our interest is as I told you that it is accentuated or enhanced by the fact that none of the Fermi liquid theory characteristics are being obeyed by this metal. And to begin with, we have said features of the Fermi liquid theory. And those features rest upon a very important concept called as the adiabatic continuation. So, there is a one-to-one correspondence between the non-interacting problem and the weakly interacting problem, and so there are a relationship, or rather there is a correspondence between the non-interacting particles and what we call as the quasi-particles. I have defined what the quasi-particles are. So, when there are particle hole excitations in the system, so there are formation of these quasi-particles, and these are called as a Landau quasi-particles. So, they are characterized by a dressed mass as opposed to a bare mass of the electrons. So, so Landau's theory rests on two ideas. One is that there are these quasi-particles that are formed, and due to the motion of the quasi-particle, the filled Fermi C that recoils back, giving rise to because of the momentum conservation and giving rise to an renormalized mass for the quasi-particles. And in addition to that, there is another thing which we do not discuss at length, that is the energy of these quasi-particles actually depends on the distribution of other quasi-particles in the system. And this Landau had taken into account by a function which is called as a f function. So, which gives rise to a Hamiltonian, this is the Landau's Hamiltonian according to the Fermi liquid theory. So, there is an epsilon k which is with respect to the Fermi energy, and then there is a nk sigma, there is a k and sigma, and then there is a factor which depends upon if it is a f n k n prime k prime and delta n k sigma. So, this is we can write it with a small fluctuation in the density. So, it is delta n k sigma and delta n prime k prime sigma. So, there is a sigma prime as well, and this is a sum over of course your k prime, k prime, sigma sigma prime and n prime, etc. So, that is the f function by which he takes into account the energy of these of these quasi-particles because of the distribution of all other quasi-particles. So, the by and large the summary of this lecture is that the whole idea of Fermi liquid theory rests upon the formation of the of the quasi-particles, and these quasi-particles are long lived. So, let us just write this point. Just to remind you that we have said that this quasi-particle wave function must be the at least the time evolution of that is represented by this epsilon I t by h cross, where because of the interaction term this energy picks up a real as well as an imaginary part. Epsilon r and epsilon I both are real, but this is the imaginary part because of this I factor, or we can write it with a minus sign, which is more meaningful in this context. And so, this becomes equal to minus epsilon r t by h cross, which is just like the particle that we have the non-interacting particles, excepting that now the energy has changed, which is given by the real part, and this is the minus epsilon I t by h cross, and that is so your the quasi-particle lifetime, that is how long these quasi-particles will live, is actually given by these epsilon i's. Okay. So, this scattering rate or decay rate or the lifetime associated with the quasi-particles are the imaginary part of the energy of these quasi-particles. So, now Landau's prediction makes an important statement about this quasi-particle lifetime, and that is called as the. So, let us just write this in full. This scattering rate or the lifetime, it goes as t square. Okay. And it is an important thing that this, if one actually can show that this scattering rate goes as the square in temperature, this is in absolute temperature, then of course, the resistivity also goes as we are not going to prove this, but these are results that we are quoting, that these quasi-particle lifetime or the scattering rate or the decay rate, whichever name you want to give it to this tau e, e for the electron, so or the quasi-particles for that matter, that goes the temperature dependence of that is this, and the rho, which is the resistivity. Now, this resistivity also goes as these quasi-particle lifetime, the temperature dependence is that of the quasi-particle lifetime, and that goes as t square as well. Now, what resistivity that we are talking about? We are here talking about the in plane resistivity. So, this is like what is called as the rho a b in the experimental language. So, this is the resistivity of the copper oxide plane, and that goes as t square. So, just to give you a small story here, that rho actually which is what you know, that the resistance of any material in 3 dimension, that goes as rho into L over A, where L is the length of the wire and A is the area of cross section, and rho is the resistivity, which is a property of the material. So, this if you do a dimension, so L has a dimension of length and A has a dimension of L square. So, this is like rho divided by L. So, it is equal to rho L minus 1. So, rho equal to R into L. So, there is a geometric factor that is there in 3 dimension. So, if you really try to understand, this goes as L to the power 2 minus d, where d is the dimension. Okay. So, because d equal to 3 or rather if we write it this way, then of course, this goes as d minus 2, d minus 2, not 2 minus d, is d minus 2. So, if d is equal to 3, then rho goes as r into L. So, there is a geometrical factor, this is that is there. However, in actual experiments, one measures R, the resistance, whereas in a theoretical sense, one wants to talk about rho, which pertains to the property of the material. So, if we need to do away with the geometry or just the external parameters, we should actually talk about rho. But however, in 2 dimension, it really does not matter, because rho is equal to R. So, there is a perfect agreement between experimentalists and theoreticians, and that is why one does not really care too much. So, this is same as the resistivity. So, the in-plane resistivity goes as T square according to Fermi liquid theory. But experiments in the high Tc superconductor shows rho a b is proportional to T. So, it is not a square of or it is not quadratic in temperature, but it goes linearly in temperature. So, this is a clear indication that Fermi liquid theory is breaking down. And if Fermi liquid theory is breaking down, one needs to understand that why is it happening. So, is it related to the fundamental assumptions that we made for the adiabatic continuation? That is, in adiabatic continuation, if you understand that we have said that there is an equivalent description of the non-interacting system with that of the interacting system, and there is a one-to-one correspondence, and not only that, there is a quantity that can be used as a marker to describe both the systems, that is the non-interacting system and the weakly interacting system, and we have said that that could be the node of the wave function. The node remains same, and there is a one-to-one correspondence between the two the non-interacting plus the non-interacting plus a weak interaction superposed these two systems. So, if that has to break down, one thing can happen is that these the quasi-particle description that we have started off with, that is this one-to-one correspondence between the non-interacting and the weakly interacting system, that may be going down, and that could be going down for two reasons. One is that the quasi-particles are no longer long-lived, they could be actually short lived and decay fast. In a way, the the scattering rate can be calculated by, this is the tau e, which is what we are talking about. It is like 2 pi h cross, and then sum over the final states, and then initial and h interaction and a final state, and this, and then there is a conservation of energy. You have to sum over the final state. So, these are final. So, this is the final state and this is the initial state, and this quantity is by and large taken as momentum and energy dependent, which is true at low energies and close to the Fermi surface. So, this tells that so this basically goes as if you want as epsilon square, and it also goes as T square. So, this is the assumption and of the Fermi liquid theory, and it says that these are at low temperature or low energies and low temperature, these are very long lived quasi-particles. But suppose that does not happen, then we have to understand why it does not happen. And one can understand it that since we are close to a phase transition, the fluctuations in the order parameters become large, and when the fluctuations become large, it becomes difficult to have these matrix elements to be having small values, and these matrix elements actually can become large, and they start depending on energies and so on, and momentum and so on, momentum transfer between the initial and the final states, and in which case these interaction terms or the interaction matrix elements between the initial and final states no longer remain small, and these tau e no longer remains infinite, or rather they sort of so this is in fact it is like the it is the inverse of that. These are basically we are talking about the inverse of that, which is these becomes large. So, this becomes small, the quasi-particle lifetime becomes small, and then the the quasi-particles are not very long lived, and they decay before the interaction must be I mean during the time the interaction is switched on. So, there is one way that the Fermi liquid theory may be not holding good or may not be valid in the normal state that we are trying to address. So, it could be happening that by the time that one is actually switching on the interaction term, all these quasi-particles decay and no longer they are valid descriptions of the system. Okay. And if they are not valid description of the system, Landau's Fermi liquid theory cannot be applied. There is another way to understand this, is the following, that if you remember that we have drawn this picture and plus a weak term like this, these are the energies and so on, and whereas these of course energies are equally spaced. And what we have shown is that there is a one-to-one correspondence between these energy levels in order for the Fermi liquid theory to hold good. And why one-to-one? Because these are the this should not go out. Of course, you understand the wave function has to vanish. I am drawing a very rough sketch, so you should okay, and so on, and then of course you have this and these are the correspondence. Now, if it happens that the correspondence can get messed up if we have a level crossing that happens somewhere. Okay. And if there is a level crossing of this kind, so while you try to connect or rather establish a one-to-one correspondence, there is a crossing of levels. So, if there is a level crossing, then at this point it is not difficult to make a decision whether we will go will take this direction or will take this direction, and these level crossings would invalidate the Fermi liquid theory, the assumptions of the Fermi liquid theory or the quasi-particle description. So, in a nutshell, that is what must be happening in the normal state of the cuprates, which has created problems in understanding it in a lucid manner and then making predictions or rather forming a complete theory out of it. There is another factor that has contributed even more seriously to the understanding of these normal state. The Hall current, as we said that the decay rate actually goes as the resistivity itself. So, if the decay rate dependence is like T, which is I think what we have written there, the decay rate dependence is as the resistivity. And now, there is also what is called as the Hall current. Okay. And this Hall current is in presence of a perpendicular, strong perpendicular magnetic field, and this Hall current, from the Hall current, the resistivity, the Hall resistivity, let us write it with a rho h, the Hall resistivity goes as T square, as a Fermi liquid character, or rather the signature of a Fermi liquid theory, whereas usual charge current, that goes as we just said, that it goes as T. So, which means that are there two kinds of quasi-particles? And it is very easy to understand that the Fermi liquid theory completely excludes such exotic ideas that there could be two kinds of quasi-particles. One would have a different temperature dependence than the other, or rather one would have properties which are different than the other, and then of course, all these basic assumptions of Fermi liquid theory, they break down. Okay. And where all Fermi liquid theory is not the only place in the normal state or the underdoped normal state of the high TC superconductors that this thing Fermi liquid theory breaks down. There are other places as well, such as quantum critical point, in the vicinity of the quantum critical point. What is a quantum critical point? We have shown you in the context of these iron based superconductors, there are quantum critical point. So, basically usually all these phase transitions that occur due to a phase transition from a disordered state to an ordered state, such as a metal to insulator or metal to superconductor transition, or a paramagnet to a ferromagnet transition. So, these are second order phase transitions, where of course, we know that these fluctuations of the order parameters become large, and which can actually impart large matrix elements of the interaction term between initial and final states, which is why we have proposed that, or rather conjectured that one of the reasons where Fermi liquid theory could be going down. But there are other kinds of phase transition, classes of phase transition, which happens at 0 temperature, which are not driven by thermal fluctuations and purely driven by quantum fluctuations. So, quantum critical point is actually going from one ordered state to another ordered state, and in that kind of phase transitions, these matrix elements between the initial and final states can actually become very large. Okay. And this would give rise to, like, there are known results that how Fermi liquid theory breaks down. Your CV goes as T log T in some near this is called quantum critical point, we will call it as QCP, and there are chi that goes as log T and so on, and then rho goes as some power of alpha, which the alpha is certainly not equal to 1, but could be 5/3 or could be 2, as we have seen in various 2, sorry, it is 1 in these so high TC superconductors. So, as I so just to summarize the whole issue is that we have talked about the high temperature superconductors, which are not conventional superconductors, which are unconventional superconductors. They have a different pairing symmetry. So, let me write down all these briefly. Mostly a d wave dx square minus y square d wave pairing symmetry. at least most of them. So, we are talking about the cuprates mainly, strong, very strong electron-electron correlation, which is understood from the parent compound being an antiferromagnetic insulator, because usually for a metallic case it is a half filled metallic band would have been observed, but because the undoped state is an antiferromagnetic insulator, this confirms that there are very large electron-electron interaction effects that are prevalent in this material. Then of course, many things such as unusual undoped state, which is what we just said, of that of an antiferromagnetic insulator, unusual underdoped normal state, the resistivity goes as T, which is as opposed to T square, which is a prediction of Fermi liquid theory. Rho h goes as T square, suggesting two kinds of quasiparticles. And in general, violation of the Landau Fermi liquid theory in most of the aspects, such as even this scattering rate, which can be determined from the optical conductivity measurements. We have not discussed that, but these scattering rates actually can be calculated from the optical conductivity measurements. They show anomalous dependencies on temperature and various other things which are have contributed to this confusion about the anomalous normal state. And because the normal state is poorly understood, one cannot actually make up a complete theory for these class of superconductors. And it nearly went on for about 30 years or 3 decades, probably a little more than that. And the research had enriched, of course, the understanding of all these superconductors, both theoretically and experimentally, but yet there is no complete understanding of the entire phenomenon of superconductivity in these classes of cuprate superconductors.